All right, let's dive into a really fascinating corner of formal logic. But look, this isn't going to be some dry, dusty lecture about memorizing rules. Nope, this is a story about creativity, about efficiency, and about how sometimes the smartest way to find the right answer is to deliberately break the rules.
It just sounds wrong, doesn't it? I mean, in a field as precise and rigorous as logic, how could a step that seems totally incorrect possibly lead to a better, more elegant, or even just a correct proof? Well, stick with me, because that completely backward-sounding idea is the whole genius we're going to unpack today.
So, first things first, we need to understand the world we're about to rebel against. And that's the world of standard, or canonical, formal proofs. You can think of these as the official, by-the-book, totally proper way of showing something is logically true. On the surface, they seem perfect, elegant even. But they've got a secret problem, a hidden flaw. And here's that flaw in a nutshell. The ideal, right, is that a proof should be this crystal clear, beautiful path to the truth. But the reality? Well, the source material makes it clear that these standard proofs often become a total tangled mess. They get bloated with all this low-level, nitpicky detail that completely buries the actual brilliant insight, the big idea at the heart of it all. It's kind of like trying to admire a masterpiece sculpture that's still covered in scaffolding. You know something amazing is in there, but you can't really see it. And, for logicians, this is just maddening. All that low-level detail doesn't just make things messy, it actively hides the core structure of the argument. And what's worse, the system makes you put the steps in a very specific order, even when that order is totally random and doesn't really matter. So you get to this crazy situation where you could have two proofs making the exact same core argument, but because of these rigid rules, they look completely different. There's just no common ground, no way to see that they're basically the same proof.
Okay, so how do you fix a problem like that? Well, it turns out you don't just tweak the system. You go beyond it entirely. And this is where we get to the core idea of non-canonicity. And it's so important to see this not as a mistake, not as an error, but as a deliberate, super strategic move to a much, much smarter way of doing things.
So what exactly is non-canonicity? Well, to put it simply, it's any proof or system that just doesn't follow that standard, rigid, step-by-step recipe. I love this analogy. A canonical proof is like following a cookbook word for word, measure for measure. A non-canonical approach? That's the master chef who knows the principles of cooking so well they can skip steps, combine others, and invent shortcuts to get to an even better dish way faster. It's about finding a better path, not just blindly following the maps someone else drew.
And you can just see the creativity exploding here. I mean, some of these methods use steps that, if you look at them in isolation, they seem totally illogical. But in the grand scheme of the proof, they work perfectly. Others just throw out the old format and turn proofs into geometric shapes. Now, you don't need to memorize these terms, really. The big takeaway is just how ingenious logicians are being to find these better, smarter paths to the truth.
So, what's the big reward for all this clever rule breaking? This is where things get really, really cool. We've seen the problem, right? And we've seen the clever solution. But what are the actual tangible payoffs? What do you get for taking these seemingly wrong steps? Well, it boils down to one absolutely incredible advantage. Radical, almost unbelievable efficiency. And I'm not just talking about making a proof a little bit shorter, a little tidier. We are talking about a completely different universe of improvement. I want you to just let this phrase from the source material sink in for a second. Non-elementarily shorter proofs. Now, that doesn't just mean a lot shorter. It's a technical term, and it means a reduction in size so massive, so astronomical, that you can't even describe the difference with a simple function. It's a leap in efficiency that is honestly hard to wrap your head around. And this chart just says it all, visually. If that giant bar is how long a standard, by-the-book proof is for some problem, that tiny, tiny little sliver next to it, that's the non-canonical proof. The difference isn't an upgrade, it's a total transformation. But it's not just about being shorter or faster. Remember that whole problem with proofs being cluttered with junk, all that scaffolding? Well, these non-canonical methods are specifically designed to strip all of that away. They help logicians zero in on what the source calls the essence of proof, that core, beautiful, logical idea finally freed from all that distracting noise. So, okay, this approach makes our existing proofs way better. But its power goes even further than that. It's actually become an essential toolkit for logicians who are trying to build entirely new proof systems, especially for logics that are, well, a little weird. These are specialized logics designed to tackle some really tough, specific problems.
And this table just gives you a little taste of how versatile that toolkit is. Again, don't worry about the jargon here. What this really shows is that for a bunch of very different and very difficult challenges in logic, like how to handle contradictions without the whole system falling apart or how to avoid certain paradoxes, there's a specific, tailor-made, non-canonical solution that gets the job done. It's like having a set of specialized keys for a bunch of really tricky locks.
So, let's pull back for a second. What does this all add up to? We've gone from a frustrating problem inside a very formal system to a whole new way of thinking. What might have started as just a clever trick to make proofs shorter has really blossomed into a new frontier for logic itself. It's redrawing the map.
So our whole journey could be summed up like this. We started with a problem. Those rigid, cluttered proofs were hiding the good stuff. The big idea was to just deliberately break the rules. The power we unlocked was that radical efficiency, which then opened up this whole new frontier for building better, smarter logical tools and gaining brand new insights.
And this is where it gets really deep. This isn't just a technical game for logicians to make their lives easier. As the source material suggests, when you start questioning the fundamental rules of how we construct a proof, you start asking much deeper philosophical questions about what a proof even is. What does it really mean for something to be logically true?
Which brings us to our final thought for the day. We've seen that even in one of the most rigid, rule-bound disciplines there is, breaking the rules can lead to more efficiency, more clarity, and deeper insight. So the question I want to leave you with is this. If the very rules of logic can be bent to find a deeper truth, what other rules out there are just waiting for us to question them?